Electric dipoles are an essential concept in the study of electromagnetism and are ubiquitous in our daily lives. They play a critical role in the functioning of electric motors, antennas, and many other devices. The concept of an electric dipole arises from the observation that electric charges can produce an electric field that can exert a force on other charges in the vicinity. When two equal and opposite charges are separated by a distance, they form an electric dipole, which is characterized by a dipole moment. The dipole moment is a vector quantity that points from the negative to the positive charge and has a magnitude equal to the product of the charge magnitude and the distance between them. Electric dipoles interact with electric fields and experience a torque or turning force that tends to align the dipole moment with the direction of the electric field. This behavior is the basis for the operation of many devices, including electric motors and antennas. The concept of electric dipoles also plays a crucial role in the study of polar molecules in chemistry. In these molecules, there is a separation of electric charge, resulting in a dipole moment that gives rise to intermolecular forces. These forces are responsible for many physical and chemical properties of molecules, including their solubility, boiling point, and reactivity. The study of electric dipoles has a wide range of applications in fields ranging from electrical engineering to chemistry and biology. Understanding the behavior of electric dipoles is crucial in the design and operation of many devices and systems, making this concept an essential aspect of modern science and technology. The electric dipole is a fundamental concept in electromagnetism that has several characteristics that define its behavior and properties. Here are some of the characteristics of an electric dipole. Dipole moment. The electric dipole moment is a vector quantity that describes the strength and orientation of the dipole. It is defined as the product of the magnitude of the charges and the distance between them. The dipole moment points from the negative to the positive charge. Polarization. An electric dipole can induce a separation of charges in nearby neutral atoms or molecules, creating a polarization. This phenomenon is responsible for the interaction of electric fields with matter and plays a crucial role in the functioning of many devices. Electric field. An electric dipole generates an electric field that varies inversely with the cube of the distance from the dipole. The electric field lines originate from the positive charge and terminate at the negative charge. Torque. An electric dipole experiences a torque when placed in an external electric field. The torque tends to align the dipole moment with the direction of the electric field. Potential energy. An electric dipole has potential energy associated with its orientation in an electric field. The potential energy depends on the dipole moment and the strength of the electric field. Radiation. An oscillating electric dipole emits electromagnetic radiation. This phenomenon is the basis for the operation of antennas and other devices that use electromagnetic waves. Overall, the electric dipole is a fundamental concept that has many important applications in electromagnetism, chemistry, and biology. Its characteristics define its behavior and properties, making it an essential concept for understanding the behavior of many physical systems. Electric dipoles have numerous applications and uses in different fields of science and technology. Here are some of the most important applications and uses of electric dipoles. Electric motors. Electric motors work on the principle of interaction between electric dipoles in a magnetic field. When an electric current is passed through a coil, it generates a magnetic field that interacts with the magnetic field of a permanent magnet, creating a torque that rotates the motor. Antennas. Antennas use oscillating electric dipoles to emit and receive electromagnetic radiation, including radio waves, microwaves, and light. Polar molecules. Polar molecules, such as water and ammonia, have electric dipoles that give rise to intermolecular forces. These forces are responsible for many physical and chemical properties of molecules, including their solubility, boiling point, and reactivity. Capacitors. Capacitors are electronic components that store electric charge. They work by separating electric charges on two plates, creating an electric dipole that stores potential energy. Spectroscopy. Spectroscopy techniques, such as infrared and Raman spectroscopy, rely on the interaction of electromagnetic radiation with polar molecules. These techniques are used to study the composition and structure of materials, including organic compounds and proteins. Polarization imaging. Polarization imaging is a technique that uses the polarization properties of light to create images of biological tissues. This technique is used in medical diagnosis and research. Quantum computing. Quantum computing relies on the manipulation of quantum states, including the orientation of electric dipoles. The dipole moment of a molecule can be used as a quantum bit, or qubit, in quantum computing. Overall, the applications and uses of electric dipoles are diverse and far-reaching, making them an essential concept in many areas of science and technology.